Check it out now, y'all.
nanoHUB-U, online instruction.
Hello, welcome to lecture 6 of the week 5. This is the last lecture of the course. Today we are going to review what we learned this week and at the end try to connect to the whole last 4 weeks of the class. So what we did in this week is we started by looking at the analogy and the differences between a thermionic device and a superlattice type of device. And the basic idea is when cathode and anode are separated by a material where the electron mean free path is on the order of the size of the barrier, then the transport ballistic nonlinear, you have to use Landauer time formalism. But if you have lots of these barriers and this can be considered as an effective medium, then the separation between thermoelectric and thermionic disappears and you can define an effective Seebeck coefficient. One thing we also noted is that pictures and the energy space are really incomplete. To understand what happens to electron, you need to look at momentum space, so things like lateral momentum conservation comes in. And that's an important impact on the device efficiency. Then in lecture 2 of this week, we looked at an example of an embedded nanoparticle system in a semiconductor. Erbium arsenide in InGaAs was a very kind of a beautiful example of how adding a couple of nanoparticles or certain percentage of nanoparticles affected. The first impact is thermoconductivity could be reduced below the alloy limit because of the scattering of long wavelength phonons. The nanoparticles could give electrons, so there is an enhancement in electrical transport possible. And we also finished with some theoretical analysis that the potential distribution around the nanoparticles play a big role, because basically the spatial Fourier transform of this scattering term is what gives rise to energy dependence of the electron scattering, and that's an important factor to determine the Seebeck coefficient. Then in lecture 3, we went back to fundamentals. If one wants to optimize Z, which is Seebeck coefficient squared times electrical conductivity divided by thermoconductivity, what does this mean from a material point of view? What it means is that you want, in the simplest picture, a material with high mobility, low lattice thermoconductivity, and high effective mass. High effective mass came because of the density of states and the symmetry of the density of states, the transport distribution function near the Fermi function. But this can be further refined that we discuss in the lecture. For getting low lattice thermoconductivity, the parameter that comes in is standard kind of phonon limited transport when the thermoconductivity is limited by the Umklapp effects. You need typically material with low melting temperature, low density, large lattice constants, high mean atomic weights, and high Gruneisen parameter, which is the phonon scattering parameter. Then you saw how the Boltzmann transport can be solved using a nanoHUB tool. In the tutorial and the homework, you were able to practice with this. You can input material parameters with different band parameters, and at the end it gives you a graphical representation of how density of states and this transport distribution function look like, where is the position of the Fermi. Even visually you can see how large is the Seebeck coefficient, but you can get quantitative data to compare with experimental results. Then we turned into the question of what is the optimum band structure for thermoelectric. That's a complex kind of questions. Two viewpoints, important one. One of them is Chang-Wook Jong, Russell Kim, and Mark Lundström, who recently published results of how ZT power factor and various components of the power factor and the ZT change as a function of the width of the band in certain limits. when the lattice thermoconductivity is 0 or non-zero. There was also the work of Jerry Mahan and colleagues about the optimum band gap of thermoelectrics. The rule of thumbs that today is accepted is you need band gaps on the order of 6 to 10 times kT, but the fact that in some cases there is no optimum needs to be kept in mind, is that these general rules of thumb apply for a specific scattering mechanism dominating the transport. Then we went on to describe what is the state-of-the-art thermoelectric material, a ZT of 2.2, and basically the high ZT at high temperature were achieved by having two type of nanoparticle or scattering centers. One is things at the nanoscale, a couple of nanometer, and the other one using the grains at micron scale. And that's how this high performance was achieved using the Spark Plasma Sintering type material. Then we moved into some of the more exotic thermoelectric materials. These are, for example, Oxide Thermoelectrics, sodium cobalt oxide, and the other family, where conducting layers are separated by additional materials. These are considered as kind of natural superlattices. There are some ideas that spin entropy, the fact that cobalt at different locations have, at different ionization states have different degeneracy, adds to the spin entropy, to the entropy of the electrons, and as they move. That's one parameter, but we also pointed out that the triangular lattice and the geometric frustration is important. And finally, the band structure effect has been also used to explain the results. Here is one of the recent review articles that discuss about a lot of these oxide thermoelectrics. A very recent kind of new physics has been spin Seebeck and giant spin Seebeck. The idea is under temperature differences, you can have electrons with different spin diffusing between hot and the cold side, and this phonon drag and interactions with the magnetic moment can be seen through a kind of spin pumping effect on a platinum bar, and very high Seebeck coefficients on the milli volt per Kelvin has been measured at cryogenic temperatures. That's kind of a very different physics. The idea of how this could be used for energy conversion, there are several proposals, but this is an ongoing area of research. Then we turn our attention to resonant state thermoelectrics. This is a case where sharp features in the density of states can be developed because of the specific resonant states in the lattice, and this has been shown to improve the ZT. But then we also discuss that if you have the opportunity to have multiple bands, based on the recent work by Jeff Snyder et al., it's possible to reach similar results or even higher ZTs using multiple bands. Then one of the last areas that we discussed this week was going back to the single level thermoelectrics. If I have a single atom in contact with two reservoirs and I consider the broadening that happens because of this coupling, this is exactly the type of Landauer formalism that Professor Datta introduced in week 1. Then you can see that as a function of this coupling, if this broadening is very narrow, you can get high efficiencies but very small output power. At optimum broadening, you get the highest output power, but the efficiency is lower than what would be the Carnot limit, and that was the opportunity we introduced the Corzon-Alban limit for efficiency at maximum output power. Another perspective, again, each representation has advantages, give you an idea, but also a limitation, was the idea that when you connect hot and cold reservoirs for N or P-type materials, there is a single energy level at which the occupation probability is on the both sides is the same, even though there is a temperature difference and even though there is a voltage difference. And this if the two states are connected by this energy level, there is no net transfer of charge. And in this paper by Humphrey and Linke, it was shown that you can get close to Carnot efficiency if you operate with this type of resonances. Then on some of the open problems in the last lecture, we mentioned example of looking at instead of ZT versus temperature, what is some sort of equivalent ratio between heat capacity at constant volume and constant pressure for Freon gas or various type of working fluid used in mechanical engines. The idea was latent heat plays a big role, and we need to kind of, if we can have similar type of phase transition for electrons, we could benefit for energy conversion. But the idea that ZT or 1 plus ZT is related to these type of ratios of heat capacities or these thermodynamic parameters, it's something that needs to be considered more carefully. A different analysis by Sriram Shastri has shown that really ZT divided 1 plus ZT plays a key role. That's a coupling between charge and energy density. This is the similar type of strong coupling that happens in superfluidic helium by the factor between heat capacity at constant pressure and volumes. So again, these are open areas we haven't explored as much, but materials with high ZT where this coupling is strong are interesting areas where one could consider this coupled transport. One last kind of open problem we discussed had to do with the thermoconductivity of superlattices. There has been lots of theories by various groups that can explain specific results for thermoconductivity for certain superlattice or multi-layer materials based on specular reflection or diffuse reflection and so on. But really there is no comprehensive theory that tell you predictively if you can beat the alloy limit or not. And here was an example of our trials with silicon and silicon germanium where we were not able to beat the alloy limit when we changed the superlattice periods or many other parameters. And when we were able to get very low thermoconductivity, then we didn't have good superlattice. So really keeping good quality superlattice, reducing thermoconductivity is an open question. And finally, we discuss some ideas that you can have an Opto thermoelectric device. These are kind of nothing that has been done in practice, but whenever you take entropy from one location, if you could generate the entropy not by electrons, by photons, it's possible to transport them over longer distances. So this may have better performance as a standard thermoelectric. These are all proposals at this stage. I want to finish with basically referring to one or two good additional review articles. One of them is by Mercuric and Adzitis group, where he described a good summary of new and old concept in thermoelectrics. So the materials that we already know, bismuth telluride, lead telluride, silicon germanium are here, but then he provide a summary of what has happened with scaturudite, zinc antimonide. We didn't have time to talk about it. All of his group work on chalcogenides, such as last material or low temperature cesium bismuth telluride. And another material system with success is nano bismuth telluride. And at high temperatures are Zintl phase material. These two are the ones that I want to quickly introduce them here as a kind of for completeness. You can look at these review articles or the original research articles to see how they work. The Zintl phase material, ytterbium manganese antimonide, has a very low thermoconductivity because of a large lattice constant, structural complexity, and ionic character of bounding. This is different from a lot of the existing thermoelectric, but the ZT of 1 at 1200 is quite high, and it's possible that it could replace p-type silicon germanium for space applications. Another area where there has been a lot of activity is when the material is already a good thermoelectric, we enhance it using nano structures such as Spark Plasma Sintering. This is what you saw for the material with ZT of 2.2, but the real interest in this came out by original work by Ziyang Ren, Gang Chen, Melinda Risselhaus, and colleagues, where they showed for the first time for bismuth telluride that standard bismuth telluride with ZT of 1 can be enhanced to ZT of 1.4 by lowering thermoconductivity, creating nanostructure using Spark Plasma Sintering. One of the unique things about that article was not only they showed material property, they actually showed a single leg where the cooling was significantly enhanced compared to the standard bismuth telluride. One last review article I want to mention is the one by Jeff Snyder and Eric Toberer on complex thermoelectric material. It is not comprehensive overview of all thermoelectric, but it provides some of the basic building blocks to get good thermoelectric. Here, for example, an interesting graph showing thermal conductivity versus temperature for various complex materials, and how the different complexity of the lattice is used to get very low thermal conductivity. So what we did in this week 5 is we look at thermoelectric versus thermionic. In lecture 1, we did detailed analysis of arsenide nanoparticles as a model system of embedded nanoparticles in a semiconductor, how phonon thermal conductivity could be reduced, but also the effect of doping and energy dependence of scattering. Then we talked about optimum band structures and the classical thermoelectrics very briefly. We spent quite a bit of time just to review what are the characteristics of the state-of-the-art chalcogenides, ZT 2.2, which is the highest value up to date. Then in lecture 4, we look at the new thermoelectric materials, again 1 or 2 graph each, scatterdite sites. Today we briefly mentioned Zintl phase and nanocomposites are important not to neglect. Spin, Seebeck, and resonant state are some of the new physics. And then in the last lecture we went back to the single level thermoelectrics, Carnot versus Corzon-Arban, and some open questions that could be interesting topics for research. Here I want to give you an overview of what you have seen during the course and how we can connect everything from beginning. You started by looking at from atom picture of having two reservoirs at two different chemical potentials, two different temperatures. By calculating the electrical current and the heat current, Professor Datta showed how the two can be coupled, how you can derive thermoelectric effects, Seebeck, Peltier effect, and even important relations such as Kelvin relations can be derived using the fundamental understanding of a single level atom. Then we looked at how these transport models can be generalized in Professor Lundström's lectures using Landauer formalism. The important aspect there was that you can treat electrons and phonons quite similarly, all the way from ballistic to diffusive, but using the same formalism. Even though usually people who study phonon transport thermoconductivity or people who study electron transport and electrical conductivity are two different communities, really the underlying formalism, this Landauer formalism, it's quite general and can be looked at for both carriers. And for thermoelectrics, you need to do that because that's what is happening in the material. Once you had the basic understanding of the transport and the underlying equations, we started in week 3 to look at what are some of the experimental effects. The big issue is, first, how do you actually measure temperature at the smallest scale? How do you measure thermoelectric effect? And what are some of the limitations? In the homeworks in week 3, what we learned and what was an important aspect is experimental data of real thin film thermoelectric properties, temperature properties could be analyzed, and you extract the material property. Then in week 4 and 5, we looked at thermoelectrics from a broader perspective of what are the system constraints. At the end, if you want to make a cooling on a chip or you want to make power generation in a power plant, how you should optimize it. So it's important to consider the system constraint, what are the system boundary conditions. The homework in week 4 allowed us to go into changing the parameters of the system and then looking at different material properties and the impact they could have on energy conversion. The last week was focused on more a newer concept, what some of the latest material development in thermoelectrics have been. In addition to conventional thermoelectrics, we went back to the latest advances, what have happened in the last 10-15 years. There we try to emphasize what is the fundamental optimization that one needs to keep in mind. What is the optimum band gap? What is the optimum band structure? In some sense, that actually went back to the week 1, because when you want to think about that way, it's good to go back to the original single atom picture and see how things could be optimized. We finished by some of the open problems in the field. Of course, there are many other problems. This is only just one perspective. We really appreciate you taking part in this course. We hope to hear from you what are the comments, how we could improve this, or you have specific questions on something that was not clear. We look forward to continue the discussions. Thanks for your attention.